What we have is thing like this. So basically, a disk that has mass. So this is mass of the disk, and then it has a radius r. Okay. So in this example, we have rigid object, right? The disk that has moment of inertia for the, remember, for the disk is 1/2 times the mass times the radius squared. This is mass of the disk. So this is the moment of inertia for a disk. Now we're going to make the problem a little bit interesting, but having an object. So let's say we have an object which is going to be an apple. So let's say here's an object, right? Connected by to this disk. So there's a string wrapped around it, and then you have basically an apple on the other side, so connected. One thing we have here is we have basically an experiment that's kind of like a frozen in time, like this. So this is basically at t equals 0. The disk is not rotating, and the apple basically an object, right, with mass m, let's say, just sitting there at rest. And then what we do, we start the experiment. So innovating like this. So there's another string like this, keeps the system in equilibrium, and then we cut it in, we cut the string, then apple falls down and makes the disk rotate. Okay. But one thing we have here is thing like this. So starting from here, I have the object starting from rest, and then it's gonna, fall down. And it's gonna fall down. So then it's connected to the string gonna exert force or exert torque on the disk, and this gonna start rotating. That means at t equals 0, what I can say here is then the velocity of the object, I'm going to put this as O for the object, is equals to 0. So initial velocity of the object. So also what I have here is the disk is not rotating. So technically omega initially is 0 as well, right? And object starts with some height h from the ground. Okay. Now, one thing we'll do here is we're going to look at this problem from two different point of view. Okay, so I'm going to start with rotational dynamics and kinematics. And basically, so technically linear kinematics. So rotational dynamics and linear kinematics. Because what I have here is this. So as soon as we let go of the system, object gonna start falling down. But this is not a free fall because the object is connected by a string. So it's gonna just basically, slowly fall down. What I can do here is I can look at this to be my initial position, and I can look at this to be my final position. That means object undergoes the displacement delta y, which is basically its height h. Then starting from 0, one of the things I can do here is I can basically measure the time it takes for the object to go from initial position to final position. Basically, how long does it take for it to fall? Then using the linear kinematic equation, delta y is equals to v initial times t, then plus 1/2 at squared. Remember this kinematic equation. I can use this. Well, this is 0 since it starts from rest. But then I have delta y is equals to then 1/2 at squared. I can use this equation if I have the displacement, if I can measure delta y, and if I can measure the time, I can rearrange this and find the acceleration. But the way we will do here is, use this equation. I will show, let's say, what we can do. Equals 1/2 at squared. The way we can find it is basically experimentally speaking, right? So look at the position of the object every, let's say half, 0.1 second interval or something like that, right? And then have a data table, where I can have then the, distance and time. So let's say 0, 0, And then this will be y1, y2, y3, y4, y5, and so on and so forth. So I can, measure the time of position, right, at some specific time, let's say, right? So that means, get some of those values. And then I can use this equation to plot like we did before. That means if I'm looking at this as being the position y, and this is time t, so then one of the things I can do here is I can see that I can take the data and plot it and basically get the acceleration from here. Okay. So now you have there are two things you can do, right? So you can do y versus t. In that case, you're going to get something like this. So then you can, in a way, use the, a quadratic, right, fit and find then, the slope. But if you're using that, nothing wrong with that, as long as you get the right fit. In this particular case, you're going to get the slope in a pivot graph. So let's say A is the slope in the pivot graph. So that means if I'm doing y equals 1, remember, y equals mx, which translates from my equation as delta y, like basically this displacement, right, equals 1/2 times acceleration times t square. You can see, right, probably the best way to go around is do this. If I plot this as t square, I'm going to get a straight line. Remember, we did this, similar experiment, right? If I do that, I'm going to get a straight line. And in that case, my slope, m, is directly can give me acceleration because it's going to be equals to 1/2 times a. So I can find acceleration from here, which is going to be 2 times the slope of the line. Okay. So this is basically how we can find the acceleration of the falling object. Now, why do we need that? Well, we need that because we can relate this to, let's say, other things. For example, let's say mass of the disk is unknown and I need to find it. Okay. So one of the things that I can do here is I can then apply rotational dynamics to find mass of the disk. Because remember, kinematics doesn't have any information about mass of any object. It's just position, velocity, acceleration, time, and things like that. No information about mass. So if I want to find the mass of the disk, I need to go to the rotational dynamics. All right, so now what do we do in order to get the rotational, use the rotational dynamics to get the disk? Well, if I go back to this experiment, so like let's say from the start. By the way, if you have any question at any time, let me know. Any question up to this point? All right. So let's say if this is the disk, here's the object, right? So let's say, so what I have here is this. I can look at this in terms of two systems. Here's my system, which is the object that's going to move linearly. And then this is my second system, which is a rotating disk. Okay. So if I'm looking at this system one, what I have here is object that has gravitational force acting on it, and it has a tension force acting on it. So gravitational force down, tension up, but there's an acceleration downward. So it is accelerating. What I have then, if I'm looking at the equation for the system one, is the gravitational force minus tension force equals mass times acceleration, which is basically mg minus f of t equals mass of the object, right, times acceleration. This is all in terms of the object. Okay. Then I look at my system two. Well, system two is not a, not an object that moves linearly, but a disk that is just going to be rotating. And this disk is going to be rotating because of the force acting on it. That means if I'm looking at this system two, what I have here is then this is the let's say, a disk that has a force acting on it, and that's the tension force, right, that rotates the disk. With respect to its axis of rotation, it is acting exactly one radius distance from the axis of rotation, and it gives us torque. And that means rotational dynamics tells us that net torque is equals to I times alpha, where I is the moment of inertia of the disk, alpha is angular acceleration. So this is the rotational kind of equivalent to this equation, right? The net force equals ma. This is net torque equals I alpha. Well, I only have one force. Remember, torque is then the force times distance, so Ft times r. And then this is equals to, then I have moment of inertia times the angular acceleration. That means this is basically, I can write it as 1/2 mass of the disks times the radius squared, then times acceleration. But acceleration, alpha, is equals to linear acceleration divided by radius. Now, if I rewrite that, that means becomes linear acceleration divided by the radius. So this cancels with that, and then this cancels with this. And what I get here is it's f of t, or things like that. I get equation 2, which is f of t equals 1/2 times mass of the disk, then times acceleration. Now, that's why you can see, right? In order for me to find any information using these two equations, I needed the acceleration, which I get, let's say, from the slope of the position versus time graph. That means, position versus time square graph. That means that's why for, first thing we do in this type of experiment, find the acceleration, because then I need that acceleration to find that. So I can use equation 1 to find the tension force, then use that to get then the mass of the disk. Okay. Or I can just basically add those two equations together, equation 1 and 2, which then eliminates tension. So then you can easily calculate, the mass of the disk. Okay. Any questions? So this is basically finding mass using torque. So this is how you find mass using torque, because this equation, right, net torque equals I alpha, allowed us to, find the mass of the disk. All right, so the next, what we do here is, again, any questions on this, guys? All right. So next we have same problem. That means we have a disk, an object, and starting from rest, object falls down, this start rotating, right? But this time we're going to use energy approach. So we're going to find mass using energy. That means I have now two objects. I have the disk and I have the object here, like let's say an apple, right? So O is for the object, D is for the disk. So that means what I have here is this. I can say that my energy is in terms of energy of the disk plus energy of the object at any, let's say at any time. Remember, energy is basically position dependent. So like, let's say. So what I can do here, I can look at in terms of, okay, so what is my energy at point A here compared to what is my energy at point B here? That means I'm going to go from point A to point B. Point A is some height above point B, right? So that means what I can say here is I can take Y position of B to be 0. So then that's my reference position. So then what I have here is that point A has some height with respect to the position B. And what I have here is, if the energy is conserved, then energy at point A is equals to energy at point B. Well, energy at point A is energy of disk at point A plus energy of object at point A then this is equals to energy of disk at point B plus, energy of object at point B, basically something like that. And then what I do, I basically look at in terms of what type of energies do I have. That means in a way, what I can see here is this. At point A, the only, look, let's say, think like this. If I'm doing this, let's say kinetic energy of disk at point A plus kinetic energy of the object at point A plus gravitational potential energy of object at point A. And because my disk never really changes its position, I can just completely ignore its, potential energy. Then this is equals to kinetic energy of my disk at point B plus kinetic energy of object at point B, then plus gravitational potential of the energy of the object at point B. That's my, sum of my different type of energies for that particular position equals to the sum of all the other type of energies for the position B. That means this is conservation of energy. Now, if my system starts from rest, that means I can say that disk has no kinetic energy to start with, and the type of kinetic energy that disk might have is a rotational kinetic energy, which is 1/2 I omega square. So, but since it's, remember I said that omega equals 0, then no rotational kinetic energy. Also, my object starts from rest, so then this is also 0. That means at point A, only energy I have is potential energy because, object has height with respect to point B. That means I can say it's object m naught gh. Then this is equals to, once the system start moving, then, when it gets to point B, it's going to have a kinetic energy. Remember, because the object is going to hit the ground with some impact speed, and then the disk is rotating with some, angular velocity at that instant. So then there's a kinetic energy of the disk, 1/2 I omega square, plus then there's a linear kinetic energy for the object, 1/2 m object v, let's say b square. But there is no gravitational potential energy because position B here is at my reference position. That means what I have here is this equation. Potential energy at point A, then basically converted into two types of kinetic energy. One is rotational, the other one is linear. This is, the object moving down. This is the disk rotating. Okay. Then from here, what we can do is this. Mass of the object times GH equals 1/2. Moment of inertia, remember, is 1/2 mass of the disk times the radius of the disk square, then omega b square, then plus 1/2 mass of the object vb square. That means then this is the equation then we will be using when the object basically falling down and the disk is rotating, and then we are looking at basically the energy approach. Any questions? Okay. So 1/2 I omega square, right? So then where moment of inertia of the disk again is 1/2 mass of the disk times the radius square. Now, one of the things we do here is, I'll give you a clue here, is that we take angular velocity because, let's say VB is not something terribly difficult for you, to calculate. Because if your object starts from rest, and then you should have an acceleration, let's say, and time for it to go down, then you can easily find the speed at point B using some of the dynamic, information. The idea here is then, again, to find that, but using, let's say, the energy approach, using these equations. All right, so the only thing I can say is that omega is, remember, it's like V over R radius, right? So then you can, replace this with that, or just calculate omega B, once you calculate VB. Okay. And then you can use that everything then to calculate then the mass of the disk using the second method. Any questions? All right, so you guys are awfully quiet, so I don't know if you're there or not, if you guys okay with everything I'm saying, but you know, let's I guess assume that you are. Okay. Um, Let me then give you the breakdown of the lab. So if you understand the theory of the lab, then the lab itself is relatively straightforward. So there are only a few measurements that you need to do. All right. So here's the experiment. So you can see, right? So basically, we'll test our ability to use Newton's second law for rotational, where alpha equals net torque over moment of inertia. So here's our experiment. So you have a rotating disc and an object, right? So basically an apple, hanging on the other side. The system is in equilibrium before initially, and then you start, and then it falls down. And you can see, right? So basically, then what we have here is an experiment that allows us to pretty much go back here and let's say measure, the height and thing like that. So we can come back here. You can set, you may use the data table and graph if you wish, if you make the multiple graphs throughout the lab. So you should be able to, easily, this is very similar to the lab that we did, doing the acceleration. So here you have then, let's say this will be distance. And this is, let's say, the time. So let's say meters. This is seconds. So you can see, right? Here's a timer. And let's say if I sync it with the motion, I can then basically have the position and time. I can see it goes about 7 seconds until it hits the ground or the table. And I can say that here's my time 0, 0.1, 0.2, 0.3, right? So, and so all the way to, let's say, 0.7. Then you can go back and look at, okay, so when the time was, and we're looking at the bottom of the apple, basically, more or less. So let's say if I kind of sync it with this, I can say that, all right, so when it's 0.1, the position is about roughly 3 centimeters. You'll probably be more careful. So let's say 3 centimeters. And then when time is 0.2 seconds, it is roughly, maybe like 6.2 or something like that. And then go to 0.3 is about 11 point something. And so on and so forth. Then you can come back here and say, all right, so then I'm going to do distance versus time. And you should get, you can say, right, you're basically getting parabola. So one thing you can do, you can make a table here and say, all right, so this is going to be my time square in seconds square. So t square, right? And then say this is just nothing but time squared. So because this is going to give you a linear graph if you plot in terms of time square. There you go. You can go and fit a linear curve. You'll get more linear if you get the better data. And then this is your slope, which is basically your acceleration. 132 meter per second. Quite a lot, but I don't think I did the correction here. So it's basically this is 0.03, 0.062, 0.13, like that. Now I have much better, because I had the wrong unit. So it's 1.32 meter per second square. There you go. All right, any questions on how do we get acceleration? All right. So then the second one is then this is where you do all your work. So going, over things that I explained, find the tension, then find the mass. And once you do finish calculating the mass, so then you go and calculate the same thing using the energy approach. So basically this is kind of like looking at the energy and then do the percent difference. Now, here's the thing. We have different objects, right? So apple and the blue sphere. So you can do one or the other, doesn't matter. Okay. So you can do one or the other, and you just basically get mass of you just make sure that you guys are, indicating which object you are using. And then, calculate either mass of the object of the apple or mass of this blue sphere. Let me do this. All right. Any questions?
I have a question just about calculating the moment of inertia for the apple because it doesn't fit with any of the standard shapes. Should we just be using 1/2 mr squared like a cylinder, or should we use a sphere?
You don't need to calculate moment of inertia of an apple at all. Apple is not a rotating object. It's just falling down.
Oh, yeah. Okay. Thanks.
No problem. So what you need to do here is just basically get the, let's say, the diameter of the disk, which then can give you the radius of the disk. All right. But one of the things you notice probably that in most of my equations, even the radius ends up being canceled out everywhere. So if you kind of, if you look at over here, see if you replace omega with V over R squared cancels out. So this entire equation, the energy equation has no R. If I go up and look at torque equation, again, R cancels out. So let's say in this equation too, when I'm doing force times R, force times distance, right, which is R, and then on the other side, I have 1/2 m d R squared and A over R, then R also cancels out. So my equation just becomes, so F of T times R equals 1/2 mass of the disk. And I only need this because this is the only rotating object. So then A over R. So you can say, right, this is then, this cancels that and this cancels this. So no R at all. So you don't even technically need to do that unless you specifically want to find something like, I don't even see like where you actually need the radius for this particular example. All right. All right. But good question. Anything else? So that's it. So should be pretty straightforward, but I think this is a nice lab because it gives you a way of looking at, rotating object, falling object, how to relate linear kinematics to the, angular variables and things like that. So at least in terms of that, you should be able to see all that visually. All right, so that's it for the lab.